Hello, everyone. Super happy to be here with you today to discuss how we can build things, build software, services, um, applications faster while keeping the security and safety on top of our mind. First of all, thanks to Conf42 Cloud Native Conference for allowing me to be here with you today. And quick intro, I am Mohammed. I'm backend developer in Spotify, and I'm also a Google developer expert in cloud technologies. And let's the fun begin. So we all know that the demand for speed and innovation is basically everywhere. Users nowadays no longer wants to wait for weeks, or even days to get their features shipped, to get their bug fixed, to get their new improvements released. However, that speed or that innovation or that enthusiasm to release faster can create conflict sometimes when it butts up against security. Especially that security sometimes tends to value status quo. And in some cases, the dogged hunt to increase velocity can introduce new challenges and risks, such as skipped processes, insufficient testing, insufficient security testing, and so on and so forth. And when you skip testing, you soon gonna hit a roadblock. And we all know about a company that was bragging how fast they are releasing, how fast they are innovating. They even made it one of their mottos, right? However, soon enough, they hit a roadblock. And that's to say that security is also important. Definitely, speed and velocity is required and desired. DevOps enable us to release faster, ship faster, making sure that both developers and ops are aligned to once a software is ready, ship it to our users. However, security is also important because once you break that confidence that you have or that moral relationship with your customers or clients or users, once that's broken, it's hard to get back. So that's why it's also important to keep the data of your users safe and secure. And that's what DevSecOps tries to bring to the table, basically. So DevSecOps try to make sure that the developers are doing what they do best: release introduce new features, fix bugs, improve reliability, resiliency, and improve the user experience at a whole. They enable operators to, once this improvements or a feature is ready to be deploy it as fast as possible to the users. And this is what makes DevSecOps really important, particular and important, is it try to save a seat in the table to security folks to ensure that the things that we ship and the software that we release are also secure, to ensure the safety of our users or the data of our users. So you'll probably figure it out what the remainder of the talk gonna be. Obviously, we're gonna talk about the Formula One. And quick context: during the pandemic, I was sitting back home, nothing much to do. Was trying to kill some hours, usual pandemic thing. And then I started watching Drive to Survive. So it's between a documentary and a reality TV show. It's not really a documentary and not really a reality TV show, but it tells the behind the scenes of a Formula One weekend, of a Formula One race in an entertaining manner, Netflix way. And in one of the episodes, this actually happened. So Roma, during the Bahrain Grand Prix, Roma is a Haas driver. Haas is one of the Formula One teams. Was driving super fast, 160 miles per hour. That's almost 300 kilometers per hour. Was driving super fast. Bad maneuver. Probably he hit another driver and then hit the barrier, and the car turned instantly into a fireball. Now, Roma remained there in the extreme heat in that fireball for a couple of minutes. And during that time, it was interesting to hear the thoughts of the Formula One people, because by any standard, any human standard, this is actually a death sentence and a severe accident. And the Formula One folks were also worried, and a lot of them thought that this is the end of Roma racing career, or at least it's going to have a severe injuries. However, the miracle actually happened. Roma managed to get out of the car from the fireball, from the extreme heat, on his own feet, sane and safe. This is a miracle. But it got me thinking how the FIA, which is the entity that oversees the Formula One industry or races or sport, and the teams in the Formula One value the safety of the drivers. And it got me thinking, what would happen if we design our systems, our architecture, our applications in the same way, with the same level of devotion as the Formula One folks design the cars and make regulations and architecture to make sure that the safety of the driver is ensured at any moment, even in the extreme accident. Now, throughout the documentary, they were talking about safety and little to no mentioning security. And I am not a native English speaker, so I use them interchangeably. For me, they are more or less the same. So I opened the dictionary out of curiosity to find that security actually means the state of being free from danger or threat. And that, from a software engineering point of view, is not what we're trying to achieve, right? We know that once we put a system facing the internet, there are a handful of things that are considered as danger and try to break our application and bring it to its knees. However, safety means the condition of being protected from danger, risk, or injury. And this is what we're trying to achieve, right? We know that the production system, the internet-facing application are not safe. However, we try to design our system in a safe manner, in a secure manner, build the whole design architecture, by other pieces of software like firewalls and everything to make sure this risky and unsafe environment is actually safe and ensure the safety of the data of our users, our services, and our servers. And that got me thinking that actually good architecture should allow people to move as fast as they can in a safe manner. So I started a journey to understand actually the safety regulations, the safety rules that the Formula One folks follow to ensure the safety of the drivers, and check if there are any similarities, any lessons that we can take and apply them in software engineering. And this is actually what I ended up with. There are more safety measures that the Formula One people apply, but for the sake of the time, I will limit myself to 10. I hope that I can make it. It's going to be challenging, but nevertheless, there are 5 pre-crash measures and 5 post-crash measures. And the data never lies, as the saying says, right? You can see here that as the FIA introduced more and more regulations to ensure the safety of the drivers throughout the years, you can see the number of deaths has drastically increased as well. And if we compare the number of days between fatal incidents, you can see that as we introduced more and more safety measures, the racing in the Formula One is becoming more and more safer, even if it's still a dangerous sport. But it's the regulations actually worked and helped to make the Formula One a safe sport, even if they are driving at a super fast speed. Anyway, let's the fun begin for the second time. So here, the first part, we're going to discuss 5 pre-crash measures, which are basically the things that they do and ensure before the crash, before actually even the driver get into the car, and to ensure that the driver safety is ensured. The first one is the seat belts that the Formula One drivers put, containing of a 6-point harness, which can be released by the driver with a single hand movement. This is actually what the seat belt for the Formula One car look like. It's actually 6, it contains 6 harness, and the driver cannot put it by himself, like he needs help. However, it can be released by a single push, a single click. And this is, from a software engineering perspective, similar to push to deploy analogy, which make us think of automation. Automation is really important in ensuring speed and safety as well. Automation can enable SIEM to deliver greater value, but eliminating manual efforts. Tasks like checking software vulnerabilities can be handled automatically by a bot, by a software, but by a job, by a pipeline, and that would enable to free up teams to pursue more productive and innovative pursuit and innovative tasks, obviously. Automation also can decrease manual human errors, and that's occur with manual approaches. As we all know, humans do not excel with manual work. Bots and machines excel in that, so that can help us to reduce bugs and reduce errors. So automation is actually a fundamental part in the DevSecOps movement and the DevSecOps mindset, and it enables us to release the software faster, but also make sure that those softwares are actually secure. The second thing I want to talk about is stringent dynamic, static, and load tests to ensure the safety of the drivers. And that means that they are testing the car in different conditions. When the weather is hot, when the weather is raining, when there is actually wind, when the track is hot, when the track is a little bit cold, they are testing different things, the engine, the aerodynamics, a lot of things, to make sure that they have data about the car and how it actually reacts in different conditions, to make sure that during the race day, the car, they know more, a lot of things about the car that enable them to react if a crash happened or before even the crash happened. And for software engineering, that means that it's actually the equivalent of having a trusted, repeatable, and most importantly, adversarial CI/CD pipeline enable us to effectively and repeatedly test any change to our application at any moment in time, making sure that our application goes through a stringent process to understand how it will react facing different conditions. And those conditions needs to be the same conditions that our application would need to be in production, because there is no place as production. It's the perfect place in the world, and there is where the fun happen. And that will not only engage security through the development and operation processes, but more specifically will ensure their involvement as we design this process. And this is actually DevSecOps at scale and DevSecOps at speed. Another thing we can do to ensure that we are testing our application in the same conditions that it's going to be in production is canary deployments. And canary deployments is a pattern for rolling out releases to a subset of users. So the idea here is basically to deploy the change to a small subset of servers, test it, have thresholds, both errors, latency, business errors if you want to. And once we hit those thresholds and pass over them, we basically roll back because this is not a safe release. Otherwise, we release it to the users. And the canary deployment serves basically as an early warning indicator to us with less impact or downtime, which it enables, as I mentioned, to test our application in actually production traffic where the fun is actually happening. The third thing they do or they have is the cockpit is surrounded by deformable crash protection structures. And this is how the cockpit looks like. And the thing that strikes me is that they designed the car around this structure, around this piece of structure that's its sole purpose in life is actually, or in existence, is actually to ensure the safety of the driver at all time. And from a software engineering perspective, this is similar to designing for failure. And we as developers or IT folks need to think about failure tolerance when designing our application in basically all layers. No longer can our application developers confine themselves to thinking about functionality only. We must also consider how to provide functionality in face of databases, outages, slow networks, or even outages as a whole. Something that we can do to ensure that is basically enable MTLS, for example. MTLS is mutual TLS, which basically ensure that both the client and the server as mutually connected and the traffic between them is encrypted. And this is important in a microservices architecture where both services are actually interchangeably becoming servers and client, making sure that the traffic circulating inside your cluster is encrypted. So even if an attacker manages to gain access to your cluster, has no clue what is happening, and he would need to do additional work to gain access. Another thing we can do is design our application in a micro-segmented way, and that means that we are putting the data as far away from the internet as possible, and we are ensuring that we are never exposing sensitive system data. So even if an attacker compromises the internet faces system, this structure deforms itself and contain itself, and the attacker will not have the final data, and they will have only access to the intermediate servers that are not actually sensitive, and we will make the work hard for them to gain access to the sensitive data. Moving on, before they race, driver must demonstrate they can get out of the car within 5 seconds. If the drivers cannot get out of the car before the race, under 5 seconds, goodbye. They cannot race for the day. So if you want to race, if you want to go to race, show me that you can get out of the car under 5 seconds. Similar to what would happen if a crash happened. I want you to get out of that car very fast. And from a software engineering perspective, this is similar to, this is not only designing for failures, this is actually testing for failures, right? It's actually testing for failures. And a similar discipline in software engineering is the chaos engineering. And chaos engineering, very briefly, is an approach to identify failures before they become outages. And we do that by proactively testing how our system responds under stress and their errors and their failures. And while doing that, we can identify failures before they end up in the news, basically. And nothing stops you. I mean, you can start small, right? You can design the smallest experiments possible. You can just add in some slowness in your server, add in some seconds to check how your system reacts, and then take notes about what you did know, what you didn't know, and then make fixes. And then you can grow gradually, starting adding errors, such in creating a database, a whole instance, a whole region, and then you gain confidence over the releases of your application. And then the last part in the pre-crash measures is they have constant monitoring and replacement of the tires. Look at that. It's Red Bull team. They held the world record of the fast replacement of the tires. Sorry. And look how proud they are, how happy they are, not by fixing the tires, not by trying to patch the tires, but actually by changing the tires. Why in the hell we as software engineers brag how long our servers and containers and instances have been running? What would happen if we start to challenge that mindset and start adopting the same attitude as the pit crews at the pit crews and changing the tires as fast as possible? We all know the pit versus cattle analogy, right? Which is basically means that we should not treat our service as pits, but more as cattle. Resources should be started as well and removed as well and killed and switched off as well whenever necessary, of course. But what will happen if we push this zoologic analogy to a little bit further and introducing chicken analogy? So the amount of food and the amount of resources a cattle need to raise to reach adulthood needed is 6 weeks or is more compared to the chicken, which is fewer resources obviously, and the period that it needs for a cattle to reach adulthood is 2 years, almost 24 months, compared to the chicken, which is a couple of weeks. So we are optimizing if we adopt the chicken's analogy. And the chicken analogy is similar to the container analogy, to be honest, or to be transparent. But there are other metrics that we can adopt basically to ensure the security of our system. And for that, I want to introduce an example. So imagine that you have configured and secured a production cluster. And on that cluster, basically, you are running a few mission-critical applications of your company. Now, a hacker managed to get access to your system and has gained root access of one of the nodes. Now, that alone is already bad, but the attacker started to use your node as a base to attack other nodes on your system. So he managed to hide himself, and without your knowledge, he started to attack other nodes and other servers on your cluster. So imagine now what would happen if this node is replaced. The attacker will basically need to do the same process over and over again to keep his base. Now imagine that we are repeatedly killing this node after a certain period of time, let's say 1 day. So the attacker will need to repeat the same process each and every day. So once the node is actually removed, the hacker has lost their base and they need to do the same process over and over again. That's to say that we can't backdoor a system that is constantly being ravaged. So from a security point of view, this is actually good. So we have a uptime, we have a certain amount of period that we define, and then after that we basically destroy that node and replace it with a freshly provisioned node, and that's what we call the reverse uptime. Now combine that with the base freshness of your image, which is the image that we use, which is like, imagine the OS or your container image that we use to deploy all your other images. From a security point of view, even a zero-day vulnerability, you know that the maximum amount of time to deploy or to fix all your vulnerabilities is basically the reverse uptime. So the attacker that he managed to gain access after the reverse uptime period no longer have that access since we fixed the base image and the vulnerability that he was using. So those are other metrics that we can keep in mind to ensure the safety and the security of our system. I'm running a bit behind time, so I'll be a bit faster for the 5 post-crash measures, the things that we do and ensure after the crash has happened. And the first one is the driver can be extricated from the car by lifting out the entire seat. So if the crash happens, we lift actually the entire seat if we cannot get the driver, obviously, and he cannot get out by himself, we lift out the entire seat and provide him with any measures necessary to save his life. And take a look here and notice that designing the car in a modular way enabled them in case of crisis to lift out the seat, the entire seat from the car. And this is similar to designing the car in a modular way and a less coupled way enable you to react in case of crisis and in case of incidents. And there are a lot of benefits of having a loosely coupled system. It has fewer dependencies that you need to manage and ensure the version and make sure that they are up to date and containing no vulnerability. There are failure isolation. If one node or one service failed, you have that resiliency to not fail your whole system, basically, and keep the other parts of system up and running. And evolvable architecture is a great one as well. You can evolve your system and the architecture independently, reusing other services with less and few coupling of your system. The second thing they have in the post-crash measures is a HANS system, and HANS stand for hand and neck system, that absorbs and redistributes forces that would otherwise hit the driver's skull and neck muscles. And this is how a HANS look like. It's basically when there is an incident, the force generated by these accidents are gigantic since they are moving super fast. So the hands make sure to redistribute those forces throughout the body of the driver that otherwise would basically break his neck. And this is similar in software engineer to have or design our system in an elastic way, making sure that we have a set of patterns to build our architecture in an elastic manner, such as load balancers when the traffic increases. If traffic increases and our nodes are not keeping up, we can have auto scaling to introduce more nodes. We can have request time threshold if some of the services are starting to get slow. So in some cases, having a degraded performance is better than having an outage or nothing at all. And also adopting some anti-overload patterns such as circuit breaking and exponential backoff help to alleviate some of load issues, basically. Another thing they have is driver suits are fire resistance, and they can keep the driver's body under 41 degrees for at least 11 seconds. And this is how their friend Roma managed to stay sane and safe, because his suit can keep his body under 41 degrees, even if it's in a fireball in the extreme heat. And from a security point of view, this is similar to containing the damage and to containing your attacker. And there are a couple of security principles that we can be followed to achieve that. Making sure, like adopting least privilege principle, making sure that our application services are running with the minimum set of access rights and resources enable them to perform its function. Defense in depth and having layers, basically. So even if an attacker manages to breach one layer, we have an additional layer and a second layer, many layers afterward that can make his life harder and slow him down until we figure out what's happening and fix the vulnerability. Having a zero trust policy. And zero trust means eliminating implicit trust and continuously validating every stage of digital interaction and communication between your services. And it's really important to have no implicit trust but every time requesting authorization authentication from the calling services or servers or whatever. Another thing we can do is basically having hardware security modules. And an example would help here to understand what I try to say. So imagine an attacker managed to get access to your database or to your server and extract the data from your database that contains, let's say, passwords of your user. Now, without your knowledge. So he can take that data, brute force it, manages to break it, and he would gain access of plain text of your user's password, and you will not know until you find those data in the market, in the dark internet. And you were basically using a function to hash your user's password, and he managed to break it somehow. Imagine now having a dedicated entity or a dedicated server that give you a key with which you hash the password, and you cannot encrypt the password, and you can decrypt it until you have that key to ensure, like, compare it until you have that key. Now, even if an attacker gets this data out of your cluster, he would be severely limited on the impact he can make, since he would need to stay within your cluster to get that key in order to be able to break the data and gain the passwords. So we are keeping him in and containing him until you figure out what's happening, and hopefully that can help you gain some precious minutes until you figure out what's happening. Another thing they have is basically a fire suppression system that can be activated by the driver externally or by the race marshal. So in case of a fire, the driver can trigger the system by himself. Otherwise, the race marshal can trigger it. And this is the equivalent of having access policies to your system. There are no right or bad way. Define the access policies that you want, both from communication policies between your service. If a service doesn't need access to a server, don't give him that access. Block him, basically. Each server needs to be allow listed before calling another service. For your users, having airbag policies and ACL policies. Don't be overly restricted, but don't be very optimistic as well, and very without any protection in place. And finally, they have data recorder that keeps data about everything. I've read that in each race, Formula One people, each car can generate more than 1 terabyte of data, which is a lot of data for each race. And that goes to say that no system should go to production without having monitoring and logging tools in place, especially security ones that help you to detect unusual behavior and trigger alarms and allow you to react in case of issues. I want to end this presentation by highlighting how comfortable driving a Formula One car is. Look at how the driver sits in a Formula One car. And it's actually a trade-off between security, between speed and safety, and extracting the maximum of the car. And the same thing applies for software engineering and the way we design our system. So it's basically a trade-off of our system that we need to make between security, speed, and velocity. And I want to end this presentation with a scary number from Cost of Data Breach by IBM security folks. They run analysis and found that in average, it took the cost of cyber attack is more than 4 million. However, it took more than 280 days to detect the breach, which is a long period of time. So I hope that throughout this presentation, you discovered some patterns that would help you to ensure the safety of your system, application, servers, and services while increasing your velocity and moving fast. Thank you very much. And thank you to Conf42 Cloud. I'm a little bit over time, so sorry for that. Happy to take your question if you have anything. And I'm pretty available on Slack. Those are the resources that helped me to build this presentation. And yeah, that's pretty much it. Thank you very much. And I hope you enjoyed the talk and wish you a great conference so far. Bye-bye.